So the first thing we need to do with thermodynamics is talk about two concepts that we use all the time, but don't necessarily use them in scientifically correct ways. So let's talk about heat and temperature, and specifically how both of them relate to energy. So the two goals that we set out when we first started talking about energy towards the beginning of the semester was that the two things we want to do are learn to recognize forms of energy and to keep track how it is transferred within or into and out of a system. And so in terms of the forms of energy, we've talked about kinetic energy, gravitational potential energy, elastic potential energy. We've mentioned chemical potential energy. We've said there are other energies that you will see. Thermal energy is the one that we're going to start talking about now in terms of thermodynamics. All of these are forms of energy. Transfers of energy, we have two when we think about problems thermodynamically. The first one we've been dealing with for a while, that's work. The second transfer of energy is heat. So I'll make the same argument that I have sort of all semester long, which is energy is so fundamental a thing, we don't have a great definition in words for what energy is. But we can build off that not very definition of energy to have a very clear definition of heat. And heat is a transfer of energy. So one of the things I will try to do in class to emphasize this is avoid using the word heat by itself and always try to refer to it as a transfer of energy as heat. When we think about energy and transferring it around, there are two ways to do that. The first is we can do work, which is the transfer of energy due to a force acting through a displacement in terms of how that's defined mechanically. The second, the one that we're introducing thermodynamically, is heat. It's a transfer of energy due to temperature differences. Specifically, heat is the transfer of energy from something at higher temperature to something at lower temperature. So for starters, as a sign convention, we're going to use Q when we talk about heat. So heat is represented by the letter Q. It is positive when a system takes in energy as heat. So when energy is transferred to a system as heat, the value for Q is positive. Q is negative, on the other hand, when a system gives up energy as heat. So when energy is transferred out of a system as heat, then the value of Q is negative. And so we can look at a couple of examples of this. So let's say I've got a system that's represented by this purple boundary. So what's inside the purple is my system. It sits in some environment that's represented by the green boundary. I can think about the temperature of my system and how it compares to the temperature of the environment. And if the temperature of the system is greater than the temperature of the environment, and energy can be transferred between the two of them, then what will happen is the higher temperature system is going to transfer energy as heat into the lower temperature environment. So the energy will be transferred as heat from the system to the environment. That tells me that the value for Q for the system will be negative because the system is giving up energy as heat. Q for the environment will be positive because the environment's taking in energy as heat. If I switch that around, so now the temperature of my system is less than the temperature of the environment. The system is colder than the environment that it sits in, well then energy will be transferred in the other direction. So in this case, energy will be transferred as heat from the environment to the system. So Q for the system will now be positive because the system's taking in energy as heat. Q for the environment will be negative. If my system and environment are at the same temperature, then what ends up happening is the net energy transferred between them as heat is zero. So there still may be energy transferred across this boundary. It's just that as much energy will go from the environment to the system as will go from the system to the environment. And this defines what's known as thermal equilibrium. Systems are in thermal equilibrium, or a system is in thermal equilibrium with its environment once they've reached the same temperature. and they stop exchanging energy as heat. So our definition for heat is it's a transfer of energy due to temperature differences. So what are useful definitions for temperature? Well, let's start with a very basic one. Temperature is what you measure with a thermometer. And this may seem silly, but this is known as an operational definition. What do you do to measure something is a way that you can define it. And of course, the way that we measure temperature is by using a thermometer. And even though this might seem trite, there's actually useful information here. Because when you use a thermometer, there are two things that have to happen. The first is you have to put the thermometer in contact with the system, which means there has to be a way for energy to flow into or out of the system as heat. You have to create a pathway that energy can be transferred. Creating that pathway depends in part on the materials that you choose to use. An ideal insulator is a material that does not allow thermodynamic interactions between two systems. Ideal insulator doesn't allow for energy to flow between some system and its environment. A conductor, on the other hand, is a material that does permit thermal interactions. So one of the details that we'll want to pay attention to in terms of thinking about thermodynamics problems is, have we used an insulator to close off a system in terms of its energy exchange from the rest of the universe, or do we have that system inside a conductor so that energy can be transferred into or out of that system with its surrounding environment? The second important detail that's in our operational definition here is that you have to wait. So not only do you need to create a pathway to measure the temperature with a thermometer, but that process doesn't happen instantaneously. You have to wait and allow time for energy to flow into or out of the system as heat. So both of these ideas are critical in terms of allowing that energy exchange as heat to occur. There has to be a way for that to happen, and you have to allow long enough for that to happen. So let's build on that to create a second definition. We hinted at this definition when we talked about thermal equilibrium, because the second definition that we can use is that temperature is what's the same when two systems are in thermal equilibrium. So the property that they're going to have that has to be the same if they're in thermal equilibrium is they have to be at the same temperature. If they're at the same temperature, what that means is they've been in contact long enough that you've transferred energy back and forth between those two systems so that they've now reached the same temperature. So again, here's where the two important details of our operational definition still show up. So the been in contact, you've allowed a pathway for that energy transfer to occur long enough, you've allowed the time for it to occur. The zeroth law of thermodynamics, and again it's called the zeroth law of thermodynamics because we'd already sort of created the first and second law before we realized that this one in some sense was also necessary, and it's more fundamental. The others build off this, so we came up with it last, but in trying to name it and put it in the right order, we call it the zeroth law of thermodynamics. It tells us that two systems are in thermal equilibrium with a third system. So if that's true, then they must be in thermal equilibrium with each other. So basically, if system A and system B are both in thermal equilibrium with system C, then A and B have to be in thermal equilibrium with each other. A third definition that we can create for temperature that builds off thermal equilibrium is that temperature is a measure of the spontaneous tendency of a system to give up energy as heat. What this means is that energy always flows from hot objects at high temperature, to cold objects at low temperature. We'll see that this comes from the second law of thermodynamics, but in terms of thinking about temperature, what it means is that if I have two systems, the system on the left is at temperature T1, the system's on the left at temperature T2, and I know that energy is transferred from T1 to T2 as heat. So the energy exchange here goes from T1 to T2, then that tells me I know which one has to be the hotter temperature and which one has to be the colder. There is effectively zero possibility that something that is cold is going to give up energy as heat. The only way that will happen is if you take that cold thing and put it in contact with something that's even colder. So the colder you make something, the lower its temperature is, the less likely it is that that will be the system that gives up energy as heat when you put it in contact with something else. So the last useful definition that we'll talk about for temperature is that temperature is a measure of the thermal energy of a system. There's a particular very simple system we can talk about where seeing how temperature measures thermal energy is relatively straightforward. And that's dealing with a monatomic ideal gas. So in a monatomic ideal gas, what you have basically particles that are simply bouncing around. It's like ping pong balls in a box. But what the temperature measures is the average translational kinetic energy of the particles. So what you see is that if on average your particles are moving around faster, then that indicates that you have a higher temperature. So that temperature is measuring the thermal energy of your system that we think of for a simple system like a monatomic ideal gas as the average translational kinetic energy of the particles. As I make my system more complicated, again, there end up being more forms of energy that thermal energy is measuring. So if I have a diatomic or triatomic ideal gas, then not only is the temperature measuring the average translational kinetic energy, but it's also now measuring average vibrational and rotational kinetic energies. So again, you make your particles more complicated, then you've allowed more complicated kinetic energies that you need to keep track of in terms of measuring the thermal energy of a system. Solids, they sit within a lattice structure, but again, they sit within a lattice structure as if they're connected by springs. So the atoms within a solid vibrate, and with a solid, again, your temperature is measuring kinetic energy represented by those vibrations and the potential energy between those bonds within a solid. So in each of these cases, what the temperature is measuring is simply the thermal energy present with your system.